All right, folks, I think it's time to get started. So we're going to get started very momentarily with our lightning talks from all the awesome work that people contributed to the workshop. I really think we got some fantastic contributions, and I'm really excited to hear more about them. So we've got only an hour for it, though. We've got, in theory, 16 talks, although I think 2 aren't here. So the way we're going to do this, is all of the talks are numbered on the website. And every title slide has a number on it. So when you are the next person up, if talk number 3 is speaking, author number 4 should be standing right there ready to take over. I'm also going to be absolutely ruthless with the 3-minute time limit. I will play a loud, obnoxious sound when your time is up, and we will usher you off stage. So just keep that in mind. The last thing I'll say before that is 2 things, actually. After this, we will head straight to the poster plaza where everyone will give their posters. I heard there's some confusion with prior workshops still having posters up. We are authorized to use the poster stands listed on the website. So if there's a poster on the stand you want to use, just politely try to take it down and roll it up and put it right there and put up your poster. The last thing I will say is we're giving 2 awards at this workshop. One of them is the Best Poster Award that the organizers will judge, but the other is an Audience Choice Award, and everyone will vote for this award by submitting their preference at this URL. This is a Google form. It requires you to sign into your email, so in theory, you should only be able to vote once. Don't sign into multiple emails, please. I think that's all the business. So with that, can I have paper number 1 please come up? You can use this little pointer if you want.
Okay, can you remind me if there's only 1 minute left?
Yes, I'll give everybody a 1-minute warning. I will sit over here and give you a loud 1 minute.
Should I go to my contact?
Please do.
Yeah,
Please do.
You have a circle for us to stand.
I think you can use your judge.
It's a red bullseye tire.
Yeah.
Okay.
All right.
Yeah.
And I'm going to start your 3 minutes. Go ahead.
Okay. So hi everyone. I'm Fengzi. I'm a PhD student from Caltech, and today I'm presenting the morphological symmetry equivariant heterogeneous graph neural network for robotic dynamics learning. And as you see, this is a really long title, and I will explain every word later. So typically, there's a long history. Research direction is trying to bridge the model-based method and data-driven method. And one of the ways to do that is trying to inject the model information to the data-driven method. And in order to know what this information should be, we need to know what information can we help to make the training more efficient. And the first one is that we can try to inject the structural equivariance information into a robot. For rigid body system, they have kinematic chain, and this kinematic chain defines the relative correlation between each joint, and this information should be integrated. And another information is a function equivariant. So for each rigid body system, they have a lot of different components like base, joint, foot, all the joints are actuators, so they should share some same function, and in a neural network, they should share some same feature. And finally, there is a morphologic symmetry equivariant. That means for nearly all robots, they have some symmetry, left and right, and some of them even have the symmetry on the front and back. And our method is trying to integrate all this equivariant information into a neural network. And once you detecting the symmetry of the system and you get the URDF of the robot, you can automatically construct such a neural network. So this is actually a special heterogeneous graph neural network. And you can see from this graph, it is actually symmetric, but this is something called geometric symmetric. So in this case, we add another pair of encoder decoder to make it morphologic symmetry. And afterward, you can see that for each node in this graph, it has a representation of the function of it, whether it is joint, it is a foot, or it is a base. And another thing is that it also has some representation of the symmetric group of it. We test our structure on several different tasks. The first task is centroid momentum task, and the later two one is like the bottom two one are the contact detection and contact force estimation one. For the bottom two, you can clearly see that the 1 minute.
No, that's 3 minutes, but give a quick wrap up.
Okay, so just like show that the graph is really important compared with some other state-of-art method, and the one at the top just shows that like the symmetry information is really important, since if you only have the graph structure, like the performance is really silent.
Round of applause for our speaker. There we go. All right. Take it away. 3 minutes starting now.
Okay.
Okay, sorry. Don't start now. I'm going to stand up when there's 1 minute left. That will be your 1 minute flag.
Okay.
Okay.
No. Okay. So yeah, this is an uncertainty calibration for equivariant functions. I'm Eddie, and this is joint with my collaborators Jake Janessen and Robin Walters with the Geometric Learning Lab. So a lot of what we like to think about in our lab is pushing the limits of equivariant neural networks. You know, we have these nice performance guarantees, which are the SMILE, which are the provable respecting of the group symmetries in our model, in our data, but it comes at a cost of these very monstrous hand-engineered biases, and they can be exposed in a number of circumstances, such as, you know, they require very complex architectures that are non-trivial to implement. They can have limited benefits at scale. They can be compute hungry in certain circumstances. We don't have nearly the CUDA support as sort of more mainstream PyTorch libraries do. And the thing that's most interesting to us is that there's provable degradation in cases of symmetry mismatch. I alluded to this in our panel discussion earlier today when I was asking about, like, when you have a camera overlaying a grid and you have a pick and place task. If the camera is not exactly overhead the grid, then your whatever rotation equivariance doesn't exactly apply. And so as I'll be talking about, and as Yishan will be talking about in his presentation, there are lower bounds on error and regression and classification tasks. So the purpose of this work was to extend this to model uncertainty miscalibration as a performance metric that we're trying to bound. So this uncertainty miscalibration metric penalizes the discrepancy between a model's confidence and purported accuracy. So as an example, if this were a classification task, if I am 70% confident, then I should be correct 70% of the time. And so what I'm trying to explore is how equivariance can affect something like that. If this were a regression task, I could, for example, be predicting estimate and uncertainty. So yeah. So the first task I tried this was actually molecular spectra, but it actually generalizes sort of across the world. If I have a robot and I'm trying to predict a action, I don't care if it's 96% accurate, 97. I really want to know how safe it is to trust. So we come up with a definition for calibration error for a regression task. You essentially look at all the fibers induced by a prediction variance. So if I predict a variance of whatever, what is my expected error when that's my variance? Then we came up with an upper bound, which you can sort of think as the average of those errors over each of the variance predictions. And then we actually verified that the bound holds on a real data set, which was, we did it for molecular data QM9, and we're in the process of doing it for various tasks and robotics and so on.
Awesome. Beautiful. Perfect timing. All right, round of applause for our speaker. Come to the mic. All right, take it away.
Hello everyone, I'm Zhou Yuhan. I'm a PhD candidate in Tsinghua University. I'm currently also a visiting scholar in University of Michigan. Today I will introduce my work about EquiRO. It's a 4D radar odometry based on equivariant neural networks. 4D radar is considered as a promising sensor in autonomous vehicles, as it can provide high detection range, low cost, and it can detect the velocity of the objects, and it's more robust in severe weathers. Here the 4D means the XYZ spatial coordinates, and it can also detect the radial relative Doppler velocity of the object. But the 4D radar also is more sparse and noisy than traditional LiDAR point clouds. So we designed a equivariant neural network-based framework to to construct the adjacent frames of 4D radar point cloud and construct them as graphs to extract the invariant and equivariant features, and then extract the key point to perform the point registration and odometry generation. Specifically, we derive some invariant node and edge velocity features in graph by the Doppler velocity. As we know, the radar can only detect the relative velocity, so the information is insufficient for the absolute velocity. So we derive a compensated node velocity based on the Doppler velocity and the ego velocity of the radar. And we also construct edge information based on the two Doppler velocity of the 2 points, and it can be seen that the compensated node velocity is the absolute velocity of the point, and it's the projection of the absolute point to the radial direction. So it's invariant to SO3 transformation of the radar. And the edge velocity is the relative velocity, is the projection of the absolute velocity of the point at the direction of the two points. So it is invariant to SE3 transformation of the radar. So based on the two information, we can use the neural network constructed by Lee neuron and EGNN to do the feature extraction. And here are some results. We evaluate our algorithm on the NTU dataset, and it can be seen our algorithm achieves best errors in most data space. And for example, in the trajectories in the red circles, there are huge rotations, and our algorithm also achieves the best performance. Okay, thank you.
Beautiful. Thank you so much. And the next person up.
Yeah, next person come up to the front. There's a couple that are missing, but if you're next, come up to the front. Take it away.
Good afternoon. Today I will introduce some initial exploration on the equivariant non-inertial systems under guideline symmetry. As we know, the state estimation problem can be summarized to the estimation problem between arbitrary two frames. So we can do some investigations towards derive a unified formulation to unify the non-inertial systems under the guideline space and time symmetry. And we know the state and transformation representation on the direct product manifold can be formulated as the rotation and the position and the velocity between two frames. But on the Lie groups, we can define the transformation between the frame and the world inertial frame using the states of the frame, and we can derive a natural transformation definition between two frames using the group operation defined on the Lie group. Here we can find that on the guidelines group, the relative velocity state and the relative position state is different from the states defined on the direct manifold. Here, because the impact from the temporal information, the velocity could perform some impact on the position state through the time state. Here we can see that a guideline frame can be perturbed by the time variance through the velocity state. Here we can derive the general non-inertial kinematic system between arbitrary two frames, and we can derive the kinematics on the Euclidean space of the Lie algebra. for the inertial navigation system is different from the kinematic systems because the MU cannot measure the absolute acceleration. So we need to detach the gravity or gravitational field from the acceleration, and we can derive some pre-integration definitions on the Lie groups. Okay, key insight.
Real quick wrap up.
Yeah, general kinematic systems and inertial navigation system conform group of fund dynamics and linear systems on guideline symmetry groups. And we can derive the equivariant dynamics and output encoded by the space and time state. Yeah.
Beautiful. Thank you so much. Round of applause for our speaker. The rest of the questions we can save for the poster session. So our next speaker is online, so let me make sure I can help him get unmuted. Oh, I have to do it on here. That's what it is. Ask to unmute. One of the other workshops got Zoom bombed. Okay. Can we hear you?
Okay, thanks. Yeah,
Beautiful.
I can hear you. Okay,
Great.
thanks.
Sorry. Oops. Okay. So you just tell me when you
Okay.
want the next slide. Okay.
Okay,
Just say next slide.
Yeah.
All right.
Yeah, hello. Yeah.
Oh, hold on. Sorry. What did I think it'll. What did I do? Oh, got it. The Zoom thing. Sorry.
Huh.
Okay.
No
Take it away,
worries.
Yuxuan.
Okay. Hello, everyone. My name is Yu Xue, and I come from Northeastern University. I'm working on symmetry breaking problem and symmetry discovery together with my advisor, Robin. Okay, next slide.
Oh, sorry. I didn't bring that.
Next slide. Okay. So first, I want to talk about a question, just like given a function f at a group G, that's how we describe the symmetry breaking of the function f under the group G. Previous work, there's first two, the global definition and the point definition. The global definition is that for a group G, if there are all the x in the domain x that satisfy the equivariance constraint, it calls that the f has the correct equivariance, that all the x on this s is equivalent. But if there exists one g at one x, that breaks the equation. This means that this f is not equivalent to the g. This definition is very coarse, and it is globally describes the function whether there are symmetry breaking in this function. The second is a little bit fine-grained, and they are defined on the pair on the x and the g. It says that if for the given x and g pair, and if the x gx equals g fx, then for this pair it is equivalent. This has correct equivalence. And if it is not satisfied, then for this pair it is incorrect equivalence. This is too fine-grained, and it cannot demonstrate some global structure of the function f. In our case, we are defining a new symmetry breaking for this. It's just called the orbitwise definition. We are given a homogeneous space X, and it's natural to consider the orbits at the quotient space G divided X on this space. And then on each orbit, we can consider whether there's some symmetry breaking, that in each orbit, if there's some fgx equals gf fx, if they satisfied, it is the correct equivalence. There's no symmetry breaking. If it's not satisfied for this orbit, there are some symmetry breaking. So it is more fine-grained. And then I'll give you an example of this. Here is a Swiss-Roll example. And the action is just flips the z axis. The z has only two values, 0 and 1. And here the green line. Okay, sorry. Next slide.
You could do that.
Sorry. Yeah. I forget to tell the next slide. Sorry.
That's okay.
And the blue and the yellow is to decide is the label of this. For the first case, if you flip the z, if you add an invariant model, this is the invariant function of the z. For the second, if you flip the z, they will just get they will get together on the axis, so that the invariant model cannot distinguish the label for this. And in our case, we just divide propose a new case that is this is the mixed case. That in the radius it is the correct equals at the out.
Give us just a quick wrap up, Yushwan, because we're out of time.
Okay, I think it's just a like a prediction function that you can add a translation to break the symmetry at different U. In our case, we are proposed the Leo architecture to solve this optimized symmetry breaking cases. We are taking the orbit as the input to generate the symmetry breaking factor weights, and then we are proposed the three method, which is adaptive, just direct generate direct weight, or just generate a gated.
Okay, I think we'll have to take the rest to the paper because we got to move on to the next speaker.
Okay,
but thank you so much, Yushwan.
Okay, thanks. Yeah.
The power of controlling the slide projection. You can use the power. Yeah.
Which is it?
Cool. All right, take it away.
All right, hi, I'm Ethan, and I'll be presenting on linear memory, SE2 invariant attention. So in driving scenes, what do we mean by invariance? So a driving scene is going to have a bunch of objects, vehicles, pedestrians, roads, and every object has a SE2 pose. So the simplest version you could do is just like take that pose and add that as a feature, but that's not invariant at all. Another version you could do is encode like the relative positions in X and Y coordinates. That's translation invariant or like R2 invariant, but not SE2 invariant. And lastly, you can encode in the body pose frame, and that's both rotation and translation invariant. So prior works have shown that this SE2 invariance is beneficial for motion forecasting. Think about it like, if I'm trying to predict what that vehicle is going to do, it shouldn't matter where it is globally, all it matters is what's around it and how it relates to other objects. However, existing methods to do this SE2 invariant like motion forecasting have required quadratic memory because they compute this relative pose for every pair of objects. And in like large model training, having quadratic memory makes it really difficult to scale to large model sizes. Other works in like natural language processing have developed ways to do transformer attention using only linear memory, where it's still quadratic compute, but they don't have to materialize the full quadratic matrix. And this has really been one of the key things that has fueled the scaling of large language models in recent years. And some prior works, including one of the papers that will come later in this talk, have shown how to encode relative positions for abelian groups, first like 1D, like R, and then later like other abelian groups using linear memory. And so our research question is, can we do the same kind of technique, but for the non-abelian group of SE2? So we can't do it exactly, but our core method is to introduce an approximation for it. So at a high level in attention, you have like a query vector and a key vector, and you compute a dot product between them to describe the attention between the two objects. So instead of a vanilla dot product, we're going to insert a matrix in between the query and the key that is based off of the relative SE2 relative pose between those two objects. And what we describe in our work is a set of matrices to project the query and the key such that a vanilla dot product of the projected vectors is approximately equal to this like bilinear form. We show that even though we're doing an approximation, we can get approximation errors below like floating point precision pretty easily. And so in practice, it's like essentially exact. And that these methods give improvements in motion forecasting, unlike driving data sets. And for the math of this, please come see our poster because I didn't want to throw a bunch of equations.
Round of applause for our speaker. You've got 8 more seconds if you want.
All right, next speaker. Take it away.
Going down. Good afternoon. My name is Shankar Kim. I currently work with Monica Ferry in the University of Michigan, and today I'll talk about reductive linearance, a framework for GLN equivariant deep learning. So basically, in this work, we are trying to find some adjoint equivariants on the GLN groups. So that we know that current deep learning models are powerful to learn some things, but it struggles when the input undergoes some data transformations, such as scaling, sharing, rotations. And the hurdle of the problem is that a standard neural network has some nonlinear design, but it breaks the GLN equivariance. And also the GLN has a unique structure of the reductive that existing methods such as linearance has a problem of degeneracy for the GLN linear algebra. So we utilize this reductive structure to design a new bilinear, non-degenerate invariant bilinear killing form. And by designing this key recipe of nonlinearity, now we can establish non-degenerate GLN equivariance by using this non-bilinear killing form.
So we basically use this invariant killing point for all the designs of nonlinearity in our neural network. And then also I want to talk about like lifting, some interesting lifting by this map. So the question I want to like share is like, can we enable equivariant group action with our reductive linear design? So currently this neural network design is for GLN or joint equivariant, but actually if you want to solve some equivariant on the point cloud or some 3D vision data, such as some equivariant group actions, then we have to think about how we can introduce some group action equivariance using this reductive linears. And by simply by just presenting this kind of equivariant lift, now we can show that it enables the end-to-end equivariant processing of 3D geometric data. So this is a equivariant commuting diagram that explains the joint equivariance and the group action equivariance by this lifting. So by doing so, also, this is good that also we can process this in various tests, including the real 3D benchmarks. So test 1 and test 2 shows about like a simulated data set of learning some invariant functions or learning some Platonic solid classifications. So everything of these inputs are represented in the Lie algebra. And also interesting for test 3 shows that by using this group of fine invariants, now also by fusing our neural network and the SOTA of FER DGCNN, by utilizing our architecture, also it has a comparative good performance among this rotation equivariant benchmarks. Any details of the neural network design and the proof of equivariance will be on the poster. So thank you for listening, and then I hope to talk in the poster session.
Thanks so much.
There's the guy. Thank you. Hi, everyone. My name is Zijian He from Purdue University. Today, I'm presenting our work in invariant filtering for full state estimation of ground robots in non-inertial environments. This is a collaborating work with Sunny Zhu Yuan and Dr. Mani Ghaffari. Yeah, so the objective of our work is to design a real-time invariant extended common filter with full state observability. So recently, the leg and wheel robot has already shown very good locomotion and manipulation within the stationary environment. However, when the ground is moving, like the leg robot and wheel robot in a shipboard, in an airplane, there are some challenges for the state estimation. The first one is the unknown persisting and the time variant ground motion. This under this environment, the zero contact velocity assumption doesn't hold, and it's very hard to cover by the Gaussian white noise. The second one is usually this environment is enclosed with the metal shield, so there are lack of access to GPS, and there cannot access to the inertial landmarkers in the water frame. So in our work, we present invariant extended common filter that exploits the system symmetric and estimate the robot's pose and the velocity with respect to this moving environment. We analytically extend the classical leg and wheel odometry model to the moving ground and achieve full state observability under general classes of ground motion. So under our method, we have 4 reference frames: the inertial water frame, base frame, robot contact frame, and then the dynamic ground frame. So the state we are interested in are the relative orientation, position, linear velocity, as well as the contact velocity with respect to the dynamic ground. Then we utilize 2 MUs. One is from the base frame, a robot base, and then we attach an external MU on the dynamic ground. It can be placed anywhere within this environment. Then we form a relative MU motion dynamics, and then this the deterministic portion of this relative MU motion dynamics is group A phi. We also consider the contact dynamics for this to take account the potential slippage for the contact foot or the robot's contact points. This process model can be used for all the robots equipped with 1 MU on their base. Then we extend the leg odometry-based measure model from the inertial frame to the non-inertial frame, and then we found out that you still hold a red environment observation form. And then we also extend the wheel odometry-based measure model, and then it's no longer red invariant, and then we show all of the video analysis, a quick result for our experiments. We have comprehensive experiment and showcase some fully observable case in case 2 and case 5. For
Very
more
cool.
details, yeah, please check our paper and the videos.
Thank you very much. Round of applause for our speaker.
Is this?
Yep, that's the one. Yep.
Okay, hi, I'm Ho-Jin Choi. I'm going to present our work dynamic active shape model of 6D. So the problem we're trying to solve is that how can we like get the pose and shape information from stream of RGBD data? This is kind of intriguing in the sense that the pose and shape is kind of interdependent problem, and there's like partial observation includes the task of doing some kind of a shape completion. So our approach is to use the active shape model for shape variation of an object, and then use ADMM-based iterative closest point to do a constraint optimization and using a strand variation and particle filter to find the global minima of the solution. And here's me teasing the robot a little bit, like not letting it to have the object using our pipeline here. So the problem formulation is like this. So given observed point cloud and some prior shape library of an object, what we do is we formulate it as a point cloud registration problem, but the shape of source point cloud is represented as the combination of the PCA components. And then what we try to infer is the scale rotation translation, but also the shape coefficient that represent the shape of the object. So this is kind of our pipeline where we have a segmented point cloud, and then we kind of use the active shape model to get the shape and pose fitting, and afterwards we track the pose of an object. The active shape model is basically when we have a candidate for the poses, and we standardize the poses into have a canonical pose, and we standardize the point cloud as well to have a same number of points in the point cloud. We are feeding a PCA on it so that we can get a linear compression of the shape data. And then we know that like if we do a naive iterative closest point, we go to a local minima. So we use particle filter, but we use special kind of particle filter, which is the strand variation of our particle filter, which uses the low probability corresponding to the cost function of this point cloud registration problem. So here we initialize a particle, and then we are able to find the global solution of this pose and shape. And then we do a constraint ICP where we can enforce the constraint of an particle. So what we can do is we can get actually not just a single model of the pose, we can get the multiple poses candidates that can be coming from the symmetricity of an object shape. And then we can show that we can optimize the shape of an object. And then we can show that we kind of have more robustness in the occluded area scenarios. And also we optimize in the level that this each iteration particle filter runs 240 Hertz using a GPU parallelization and about 570 particles. And we tested the non-rigid case where we actually represent the object as a non-rigid different shape library. And we also show we can do unsupervised key point selection out of active shape. Thank you for listening, and hope to see you in the poster.
Great job. All right, our next speaker.
Hello, everyone. I'm very happy to present our work, the max entropy movement camera filter for polynomial system with arbitrary noise. I know this is an equivariance workshop, and you didn't say equivariance here in the title, but I want to remind everyone that the matrix league we're interested in, such as a special orthogonal group or special Canadian groups, are just a polynomially constraint space. So this is actually relevant to this workshop. The motivation of this work is that when we are solving a common filter type problems, we always assume some kind of a Gaussian assumption, such as the noise or is Gaussian, or we assume the process is linear. So under such assumptions, we have some very nice optimality guarantees for both the prediction steps and the update steps. But when it comes to nonlinear, non-Gaussian cases, we find that it's no longer to be optimum. Some solutions to fix this problem is to use the linearization, such as we do in the extended Kalman filter, or any invariant or equivariant variants, or we can do some deterministic sampling. But unfortunately, all these methods do not have some optimality guarantees. So the research question for this work is that how can we still guarantee optimality for such non-Gaussian nonlinear case. I think the harder problems for this is the belief representation as well as the marginalization steps. Our solution is mainly composed of two parts. The first part is about the belief representation, such that instead of using a Gaussian noise to represent the belief, we consider higher order moments, such that we add the mean second order covariance or the high moments to the system, we can asymptotically approximate the belief via these maximum entropy distributions. Under the condition that the distribution itself is moment determinate, we can guarantee asymptotic approximations. And for the prediction step, instead of doing marginalization steps, we actually not doing marginalization, but we propagate the moment first through the dynamics. And after that, we can recover the distribution via some convex optimizations. Given that steps, we can show that the prediction steps can still enjoy some asymptotic approximation properties. And the first plot suggests that we had add more and more moments to the systems. Actual distribution will recover the heat map of the original distribution as we show on the right plot. And we tested the algorithms on some non-Gaussian non-noise cases, such as a localization with unknown data associations. We can find that we have some unimodal assumption on the beliefs, such as all kind of common filter type work. It fails because of the multimodality. But if we consider the max entropy distributions using our work, it actually can precisely track the trajectories without any over confidence. Okay, thank you, everyone.
Take it away.
Thank you. Hi, good afternoon. I'm Jiarong Kang from University of Wisconsin-Madison. Today I'm presenting an uniform modular estimation framework that are optimization-based but incorporates the invariant properties through a decoupled orientation filter. Most existing lag robots, say estimator, focus primarily on localization. But in this abstract, we believe we can show optimization-based estimation can enhance the perception and go beyond the localization by explicitly incorporating system dynamics and constraints. With both proprioceptive and extraceptive sensors on board, we incorporate the robot dynamics and contact dynamics into the estimation framework that enables the estimation of physical quantities such as contact force and inertial parameters. And with limited understanding of symmetric properties, when we have lag robot on subject to hybrid dynamics, we use a decoupled approach where orientation is estimated via an invariant filter and the rest of the task is achieved by moving horizon estimation. Invariant extended common filter on extended special Euclidean group is used for orientation estimate. And then we have optimization-based estimator, moving horizon estimator that incorporates the system dynamics at multiple levels. MHE, which is a receding horizon optimization problem, utilize a past window of data. And in this abstract, we demonstrate three different tasks of estimation using different system dynamics. First, we have the prior work about robot state estimation using MU dynamics and robot state and force estimation using constraint Lagrangian dynamics. And in the last, we present some preliminary result on robot state, contact mode, and the physical parameter estimation where complementarity contact dynamics. And the prior results demonstrate improved performance from both extraceptive sensors and constraints. In the robot state estimation task, we did ablation starting on the window side chains. The increase of window size increased the accuracy from extraceptive sensors, and the computation only grows linearly as convex optimization. For the robot state and force estimation case, we demonstrate that by incorporating physical constraints, the feasibility of the solution can be further enhanced. And in the last, we present the preliminary result on both robot state, contact mode, and physical parameter estimation by leveraging the differential structure for efficient numerical optimization. And here we have a simple demo demonstrating a particle dropped, pushed, and slides on the frictional surface. We can see we can recover the inertial property from a biased initial gas, and at the same time, the state trajectory is updated with respect to the contact mode and in the last align with the ground truth trajectory. So in conclusion, we propose three kinds of different estimation tasks, but using a relatively modular estimation framework. And we aim to evaluate the framework on hardware for contact-rich robotic applications. And we also want to incorporate invariant residual terms into the optimization-based estimation itself. Thank you.
Great. All right, we're getting close to the end here. We got a few more.
Okay.
Take it away.
Yeah. Hello, everyone. My name is Evan Palmer, and I'll be presenting this work on behalf of myself and my co-authors, Shai Revson, Jeff Hollinger, and Ross Hatton. So rigid body systems are typically described using wrong direction.
Is that
Okay. Are typically described using point orientation representations, and these can often come with limitations such as non-Euclidean distance metrics. So to address this, what we propose is to instead use a multi-point representation that naturally encodes both the geometry of the system and also provides a convenient angle-free representation. Now, the main pitch of our work is that we propose a multi-point group structure, or we equip this representation with a group structure. An example of what this group structure kind of looks like is depicted here on the screen, where we see a right groupwise action. Now, because we're interested in characterizing the motion of multi-point systems, we also characterize the velocities of this in this multi-point group, where we have the world velocities, which is a concatenation of the two velocities for each point, and then we also have the spatial velocity, which is uses our normal definition of a point that's fixed to the rigid body system that's moving through the origin. And then we also have a nice body velocity definition, which is the relative velocity of each point along its own forward and translational axes. Now, to demonstrate the utility of our method, we apply this to a physics-informed neural network. In particular, we construct a physics-informed neural network that uses the multi-point group dynamics as inductive bias, in addition to the Newton-Euler dynamics, and that kind of gives us a formulation similar to what we see here on the screen. Now, we train it using a loss function that penalizes the position error of both points, in addition to its velocities, and we also include a soft constraint on the length of the relative displacement vector. And the results of this kind of indicate that our method is a interesting way to approach this, and also provides a nice simplification of the learning problem. In particular, we're able to show that our method is able to achieve up to about an 85% error improvements over a method that uses the point orientation representation. And in the future, what we plan to do is consider this application to 3D systems. We also want to consider better ways to naturally encode the constraint on the length of the relative displacement vector. And yeah, I think that's everything. So thanks for your time.
Take it away when we're ready.
Hi, I'm Mithun Jacob, and I'm here to talk about rope, which is better 2D and 3D position encodings with string. But before we jump into string, let's talk a little bit about transformers. So we start with the token and its position. So in language, the token is just a word, and its position is just the position in a sequence. For images, you can patchify the whole thing, and the center of each patch is the position. And if you have RGB D can become Z, or you can just make a point cloud out of the whole thing. So why are we doing all this? The main motivation for this is we want translational invariance. So if you look over there, we have Rj minus Ri. We want the loss functions of the optimization to depend on the difference between the positions and not on the actual positions themselves. So how do we formulate all this mathematically? Token is just a d-dimensional vector. In our experiments, d was 64, and the position in the examples I gave previously was just 1, 2, and 3. Last bit of transformers, we don't directly work with the x token all the time. Most of the time, it's these queries and keys, which are just the product of x with a square matrix. So what is string? A string is just a rotation matrix whose skew-symmetric generators commute. And as you can see, we applied the skew-symmetric generators and the rotation matrix to the queries and keys. So as you can see, we have Qi is equal to the rotation times W and Xi, and the same thing for the key. Why do we do this? If we have this kind of structure, then we get translational invariance in the attention, which is all you need. And as you can see over here, the attention function now has translational invariance when you take the dot product of the queries and the keys. So we did not invent using rotational matrices for positional encoding. That comes from the rope paper. And as you can see over here, that's how rope is formulated. What we do is we show that rope is a kind of string, and we provide two alternatives which are computationally more expensive but outperform rope. Also, just a note, we don't use the matrix exponential function anywhere. It's too expensive. So for more on that and more details, we can discuss that as a poster. We have a bunch of results in 2D image classification retrieval, OWLWIT. We outperform rope with robotics tasks with diffusion policies, and we implemented this on a bunch of robots, as you can see with the Aloha framework and the KUKA. So for more details, I'm happy to discuss with the poster.
Thank you. All right, take it away.
Yeah. I'm Pranav. I'm here to talk about simplification via gauge fixing in Dirac structures. I'm from the University of Oxford. This is work done alongside Aristoteles Papatheodorou, Natalia, and Yanis Avutis. This is quite an intimidating title, but I hope to simplify things by the end of this talk. Cool. Okay. So we spent all morning talking about equivariant systems and sort of some of the problems that came up where, hey, what happens when we have things like friction, control inputs? What happens to the equivariance here? One of the solutions was to sort of do this lifting, and we essentially are following along that family and sort of continuing that legacy here. So we know that physics-informed networks have performed remarkably well in various physical settings, but they have failed when it comes to sort of looking at real world settings, such as non-holonomic angular dynamics. You have sort of contact constraints, as well as friction, control input, things like that. And this is due to degeneracies in the Hamiltonian structure. Something that underlies the Hamiltonian structure is called a symplectic form, which is sort of a two form, or the area swept in the phase space, which is given by sort of generalized position and momentum. So any physical system ranging from quadrupeds to, I'm a physicist, so to quantum systems, sort of this underlying symplectic form. And we, so degeneracies in this symplectic form cause problems where you don't have these sort of geometric structures to exploit and use physics-informed networks. Cool. Okay. So the solution to this is, as suggested in the morning, we sort of perform this lift. So we do this lift. This lift is called the Dirac lift. Once we do this Dirac lift, so we actually use a flow mapping network to do this sort of in-painting where we lift this degenerate symplectic manifold to a non-degenerate symplectic manifold by introducing these two forms. I'll explain more about that in the poster. But yeah, once we do that, we have a fully symplectic network. Fully symplectic form for which we can use symplectic networks. So we can actually use a 3-layer symplectic network, something that preserves symplecticity to predict dynamics of a quadruped quite well. So these are the base dynamics as well as the information regarding the right forward. So for more information, you can scan the QR code. Yeah.
Fantastic. Thank you.